Alright, let's go teach calculus. Goodbye, Cam Ali. Mwah. Oh shoot, okay. I always say I'm gonna get there on time, and something catches me. Stupid door. You sure knows that's right? Oh, it's fun! Headed to Calc. What was that? Oh, cool. Then let's chill. Say hi to future Vaughn. Yeah, I thought, why do I have to wait till class starts to record? What was that? Say again?
You can record whatever is going to happen acoustically.
Oh. Vaughn, when you took the test, it was in 4163, right?
Yeah.
I'm going to check it. Make sure no one's using it. Okay. Very cool. So we're going to go in here. All right, you want to get that? Thank you. Okay. I started recording beforehand.
Okay. You want me to get on?
Oh, it's alright, Evan, I got it. Because I started. Chat! We have chat, that's the fourth person. Okay.
No, it's too late now. It's never too late.
No, try again. Log in. Woo!
I recorded today's video as a POV. So it starts in my office and it started recording all the way up to his. So you'll see me realizing, oh shit, it's like 5 past the hour. 5 past when I should have started getting downstairs.
Which is true.
Not everyone's there.
I knew there would be something. Oh, last week. Maybe this will be up there.
David was here.
Okay. Good morning. Last
Jesse
week
is
of
here.
anything new, this is
I can tell
insane.
Morris is here.
All right. You guys doing okay? Who's gone? People taking ASCs this morning? 1801? 1801. People taking ASCs this week.
Do you recommend?
You all know that this class doesn't make you directly jump into 1802, right? You need to take the 1801 ASC. Okay. Just making sure. Right? Anyone's mind blown by that? I just realized that that might not be obvious. But Sammy mentioned it now. I thought, oh god. Give me 1 sec.
Stand proud. You are strong with your confused teaching.
Oh, that was you? I didn't see that.
Stand proud. You are strong with your confused
I don't feel
teaching.
like
So we will teach with
Unfortunately,
rhoticism.
Oh, yeah.
My little sister had rhoticism for a while, actually. It was interesting. Rhoticism is a thing. All right. We have today's class where we're going to cover new material that will be tested in a comprehensive way. And then Wednesday, we're going to talk about a bunch of fun random topics. The idea is, like in high school when the teacher would show a movie, like you might still get tested on the movie, but it was like, who's the main actor in this movie? Oh, it was Bruce Willis. Like, that's the level of detail we'll give you for the Wednesday questions. So be chill, enjoy, learning for learning's sake. I should always be, but I get this sometimes. Today, however, we are going to need to proverbially haul ass as we finish up the two-dimensional side of line integration. So, in order to do that, I actually just remembered that back in the day, I enlisted AI in a really twisted way. I got a water bill from the city of Chelsea because I had a toilet in my property that was running wild. I thought you were taking an ASC. Your thing said James Henry.
No, I canceled it.
Oh,
Yeah.
why?
Oh no, I got the DC credit. I just signed up before.
They don't need
Oh, Mr. Tough Guy.
or you don't need them. All right. Oh, cool. I found this in James today. Good stuff. Yeah, I had a toilet. So if you ever hear a toilet hissing, you know why that's bad.
Water bill go up.
Yeah, water bill go up. Because granted, every now and then we sit in the toilet and things splash back. It's wonderful if that water is fresh and new, as was the case. It cost me $5,000 because the water to the toilet was constantly recycling. You're welcome. I said to my tenants, but it's okay, they didn't know, so we sorted it out. But the city of Chelsea sent me a water bill. I'm doing a great job of staying on top of my head. I'll show you something. Let me get the projector on. Yeah, I know, that's true. So you don't think, I thought you would think today's material was fun anyway.
No, it is fun, but like
Oh, my heart, my poor beating heart.
you said a haul ass. You didn't exactly paint it as fun.
I did not haul ass so far. Hey, there's a ring on the floor. There's a ring on the floor. It's a gold ring.
Oh, that's a grand.
No, it's not, it's
Is
hollow.
there Ryan Beal in
There's nothing on it, but that's weird. Alright. Do I have an answer?
I'm gonna grip you in the desk.
Alright, City of Chelsea, this is what happened. There was a water abatement form, and if you told the city you're sorry, you'll make sure you check your toilet leaks next time. They will forgive some of your thing. I saw that, and at the same time I was on Spotify, and in my weekly Discover playlist there was a song that I really liked. And I was a little confused because the artwork was AI generated. Then I found out the song was AI generated. It was a sobering moment. And then I realized that there was no escape. It sucks. That song actually, like, it did things to me. But I needed to get back, so I give you now my first attempt at Suno.
Oh, sing the lyrics to the policy.
And then I thought, I need to do something useful with this nonsense. And so I give you,
Salsa line integral?
I think that's what I called it. Oh, no, it's going to be in, hang on, 1802, fall 2025, 1802, audio, nope.
Music?
There's a music section?
There's a music section.
Yeah, that's what I'll get. Integrales de línea, okay. And with this, I will review what we've covered so far.
I would say this dude.
If you speak Spanish, what you manage Cuban Spanish will be okay.
But yeah, but I'm pretty sure today I sound like
Okay, I will only write what the song
Oh,
says.
Oh, that's the boss. I tried it and I got my shit.
The punto A,
I got
¿sabes?
my back.
Same voice.
I'll try it again. I don't know who I use. It is probably the best.
Okay, we got one.
I don't want to do all that. It's like, I cannot sing. You see my other teacher. But it's just such shit because
You want me to dance salsa? I'm supposed to be able to do the
I
same
have a
stuff.
full heel on
I
his.
don't.
Look, I look how the damage is. You look at all that. It's really good. But also entertaining. There's nothing I can
If there was no potential, the things get difficult. Almost there.
We're doing the We're doing the startup system. Oh, lovely. Unfortunately,
Okay. Okay. What's missing? Closed path, conservative field?
0.
Okay. And this one you derived on the P set. Not while dancing, I'm sure.
Green's theorem.
Yeah, Green's theorem. Which, yes, where's my green chalk? I'd seen it.
Behind you.
Like, what am I
Like
missing?
literally, yeah.
Oh my god, okay.
My heart is
Okay, so let's fill out Green's theorem.
The double integral
Mm-hmm.
of m in respect to dy
Yeah, dm, dy.
minus
Uh-huh.
dx d. Whoa, that sounds a little wrong.
Did I flip the order? It's dn. Ah, okay. dn, dx minus dm, dy. Okay, I had the order wrong.
dA.
dA, okay. That's Green's theorem.
It's so green.
And it's very green. And it has nothing to do with why the Green Building was named the Green Building. These are each pieces of the grand spectacle of Salsa, but also math that we were doing. This means the field does not come from a potential, so it is path dependent, and there's no way around getting it cleaner. To solve this, what do you do?
Parameterize.
Parameterize. And where are you always? I forgot to bring my button.
Always in.
Along the path, ATP. Yes, okay. Fundamental theorem
Line integrals.
of line integrals. That is the declaration of path independence. And what does that mean?
It means that there's a potential function,
Huh?
then you can just subtract the potential function.
And the 2 endpoints, like on the P sets. We have a closed path, for this reason this goes to 0. If you have a closed path and it encloses a region R, then you can find the work done along the path by finding the net or the sum of all of the little circulations inside of the region. Does everyone remember this from the P set? We proved it in the P set. Vaughn, you had a question? Oh, you got this. Okay. All right. So this is Green's theorem for work. There are a few criteria necessary to use Green's theorem. I want to review them really quickly, and then we're going to move on. So for Green's theorem, again, we have some closed path C. All right? And we have an interior of this path called R. Okay. The criteria for the path and for the field, which we've not drawn a field here. There is some field F here. The conditions are as following. The path must be piecewise smooth. That just means no discontinuities. Piecewise smooth. What was that? Simple. So no self-intersections. I wouldn't worry about that in this class because we're not going to give you some kind of funky region. Piecewise smooth, simple, closed, very important. And the last one, the most important one, the one that I will ask on, is positively oriented. Yes. This is the most important criterion because it's the one that I might actually check you on. This, I'm never going to give you something that's like this continuous. I'm not going to give you something that self-intersects. And if it's open, you should know not to use Green's theorem. But the path must be, the curve must be positively oriented. The path must be positively oriented.
Well, can't you just make it negative?
Exactly. Positively oriented means counterclockwise, but in a more general sense, it means that as you are walking along the path, the interior is on your left. Okay. Question? Hi, Lily, you got a question? Aha! So that's conditions on the path. Vaughn, I saw your hand on the periphery of my eye. I'm going to be right there. F defined everywhere in the region. All right, fun. Oh, David.
Are we, so after this, are we doing Flux?
I'm hoping that we can.
Okay.
But first we're going to learn how to find potential functions. Okay, these are the conditions to use Green's theorem. This Green's theorem is called Green's theorem for work. Otherwise known as Green's tangential form of Green's theorem. Like back in the day when old school books and movies had two titles, Calculus 3 or Massacre and 4159. Okay. Questions on the setup, on any of this? We will not make a career out of messing with you guys with the conditions for Greens, provided that you know that the path is closed, the path is positively oriented, and the field is defined everywhere inside. You are authorized to use Green's theorem.
But if it's not positively oriented, can you still continue?
Exactly. If it's negatively oriented, then what do you do? Make it negative, yeah. But we won't even mess with that.
Really?
I don't think so. You want me to mess with that?
No! Whoa. Remix. I mean, you're so grateful for your hard
Okay.
I'm so grateful for your hard work.
Oh, I love you guys. This is wonderful. I'm gonna miss you. I leave the country in like a week.
No.
Yeah.
Wait, I thought you were teaching Israel. It's weird.
I am. Sorry, I'm not moving.
Whoa.
So Redhead and I are disappearing on Saturday.
No.
We're gonna leave the country. Yeah. So this will be all right. It'll be okay. We're gonna have a party. We're gonna celebrate how much
You're gonna ruin us with the final. You're gonna go out.
And then I'm gonna walk, right? No. We'll have our end of class party on Wednesday. But I'll be around. I'll fly around this semester. You can find me. And if you take scuba diving, you will take scuba diving from Redhead because she's teaching it here in the fall. Okay. Now, big deal is how the heck do we find the potential function? Because so far, the only way that we've talked about finding the potential function is to just like guess. So two things. Number one, how do we how do we know if the field is conservative?
The inner graph, or the curl, has to be.
Ah.
That's
Yes.
why it was zero in the first place.
Right, so the field has to be the gradient of a potential function, which also ends up being that the field's curl is equal to 0. We're going to do this in 2D in this class. 1802 in the fall, we'll do it in 3D. Curl is a measure of the field circulation, and bigger, sort of stuff you'll see in 1802 is that the curl technically has a direction. But because we're keeping it 2D, the direction of the curl is the same no matter what, so we just treat it as a scalar. This is something that I call, when I teach 1802, the baby curl, like baby kale. What other? I consider eggplant. No, what's albino broccoli called?
Cauliflower?
That's the one. Yeah. Okay, so we'll leave it. This is super important, and the curl we said was what? dn? I keep forgetting, right?
dnx.
dn dx minus dm.
dny. But if f is the grad, really that's just saying fyx minus fxy.
Yes. Yeah. Mixed partials. Yeah, because if the field is the gradient of the potential function, then that's df dx. Oh my god, I'm really happy you brought that up. If the field is the gradient of a potential function, then what happens if I differentiate this with respect to y and this with respect to x?
They're equal.
They're equal because they're mixed partials, right? So, no, that's wonderful. Sometimes I forget these things, and then you guys say it.
Eureka.
Yeah, Eureka. All right. Eureka.
It's my joke. First you
Okay.
eat a tea bag, and then you...
Next up. If once we know that the field is the gradient of a potential function, how do we find f?
Well, we know then, if we keep building on the vector field is the grad, and we know that partial derivatives
Yeah.
into the game.
Did you have time to read the lecture notes before class?
Oh, no,
Because you all sound so put together.
No, it's
Like,
the
you all-
p-set. The p-set forced us to be 4D somehow in
Oh,
unconventional
yeah.
ways.
But I was hoping you would take that into scalar land and suffer less.
No.
Oh, damn. I really want to know whose ring this is. This is problematic. All right. Okay, so we're going to talk about finding the potential function. There's two methods. Which one do I want to do first?
I told you your tea bag with your spoon.
Bro, that's so mean. I know which one I want to do first, actually.
Maybe I do understand. Pucker up, buddy.
Yeah, okay, let's do it. Okay, so method number one. I forget during the semester which one I call 1 and 2. But we'll see. Okay. If the field is the gradient of a potential function, that is to say df by dx, df by dy is m comma n, then the method we're going to talk about is, it's easy for 2D, it's annoying in 3D, but since we're going to keep it to 2D, I think this is okay. Okay, if the field is the gradient of a potential function, then we have the following. Step 1, pick a variable. Pick m or n. I'm going to pick m. M is df by dx. So, normally, you see a differential equation, what do you want to do? Integrate.
Let that integrate. Whoa.
Yeah, okay, so we're saying that f of xy is the integral of df by dx, sorry. dx. Is this the whole story?
There's a plus c somewhere.
There's a plus c somewhere. There's a plus c, but this c is actually really interesting. Because in single variable calc land, a constant was anything that when you took the derivative of it with respect to x, you get 0, right? But in this beautiful world of multivariable, we have two variables. In terms of another variable, as far as another variable is concerned, derivatives go to 0. Am I saying that well? Let's see. If I take the derivative of this with respect to y, right? This constant will turn into 0, right? This constant needn't just be a number, because this is a y derivative, and in the world of partial derivatives, as far as y is concerned, what else is the constant? X. So this really is some function, not constant. I'm going to call it g of x.
Wouldn't it be g of minuses?
Silly Christian. Tricks it for kids. Yes. Because why? Because why? Because if I take the derivative of this with respect to x, what am I going to get out of this? Just m, right? I'm going to get m here. And if I take d by dx of this, partial with respect to x of any function of y, 0. Does everyone understand why then this is not just a scalar constant, but some function of y? It might just be the number 5, but it might also be 5y plus 27y squared plus y to the y power. What's up? Oh, I know you had that. Because I clipped it over here enough, I'm just telling you how to rob me at this point, and so I wouldn't even notice that I missed it. That's it. That's funny. Okay. Oops. You bet. Okay. I guess I'm giving you guys a presentation tomorrow during your 12 p.m.
Oh, sorry, what?
I don't know. What do you want to talk about? I'm very confused by Chrissy's text. We'll figure it out. Okay. So, yes, sorry. You wanted an explanation? Yeah, okay. You agree that the field has an x component and a y component, and if it's a conservative field, these are derivatives with respect to x and y. Okay. So, you know that if I integrate this with respect to x, I'm going to get the x components of the field. Right? Because m is df by dx, then integral of m dx gives me f. Almost. What's missing? There's a y component. There's a bunch of stuff with y. Because to get m, I took df by dx, right?
Why don't you try it with, for example, a 2x, 2y? Then you'll really see it.
Yeah, why don't we do that?
That's right.
Yes, no, that's good stuff. I prefer an example. Yeah, thanks you guys. Sometimes I get trapped in the theoretical stuff, and I think we should do it. So, Loyan, I'm about to answer your question with numbers. I think that would be more palatable. Okay. Let's say that the field is 2x, 2y. And we know that the field is the gradient of a potential function. So that means that m and n are themselves potential x derivative, potential y derivative, right? Okay. Okay, so then our potential function of xy is the integral of m dx. Why is that? Because m is df by dx, right? Yeah, I think I'm highlighting something I should write here. I should write this as m. Because m is df by dx. Okay, so it's the integral of this. All good. But let's do that. What do we get? That's the integral of 2x dx, which is what? X squared. All right. So the x derivative of my potential function gives me 2x. But what's another function whose x partial derivative could be 2x? X squared plus y to the fifth. What's d by dx of this? Still 2x. So our integration is only accurate up to a constant in x. And y, as far as y derivatives are concerned, is a constant in x. Okay, does that make sense? Okay. So that's what we're saying over here. This is some function of y, that's our constant. Okay. Step 2. If we know this is our, if we know that this is our potential function, what don't we know? What remains unknown? We did this fine. We don't know what g of y is, right? It's just some arbitrary constant. Okay. So, well, but we do know something. What happens if I take the derivative of this with respect to y? What should I get? N, or 2y in that example. Now, do df of xy dy. We know that should be equal to, you guys just said, to n, to 2y. Yeah. If we do df of xy by dy, I think I'm going to need to get a little bit more room, so let's bring the projector back. If we do d by dy of df of xy, we're going to get the y derivative of this, which we have already found, so we can take y derivatives, no problem, plus dg by dy. Okay. We don't know what g is, we don't know what dg by dy is, but we know that this whole thing should be equal to n, the y components of the field. So we match terms to find dg. Okay, that leaves step 3. If we have dg by dy, how do we get g of y? To get g of y, what do we do? Integrate, yeah. So we integrate dg by dy, dy. Now we have g of y, and our potential function is complete because we know whatever this is going to be, and we have just found g of y. And we can add a constant. We'll do an example. But that's the general idea. All right. So, pick an example that'll get along. But the idea is integrate, differentiate, integrate again. And what's the best thing about these kinds of problems? Once you find the potential function, what can you do to make sure you are not wrong? Plug it back in, take its gradient, and if you have a field, then you're definitely onto something. Okay. So let's do say the field is x plus y squared, 2xy plus 3y squared. So first part, this could very easily be a problem that you see at some point. I don't know what point is left to see it. Can't think of any single reason you might see a problem like this. Check if f is conservative. And if yes, find the potential function. Take a minute to work this out, and we will have at it together in a second. What is 32 going to? Static problem.
Booking 32, no, booking 32 is like by is t. Because 34 is by is t, so it's like the one that's 32 is that.
32.
Oh, 34?
Yeah, it's in your
Did you get it? Yeah, wait. I just want to go home.
Yes. I ordered something on Amazon from my office, and they left it at some random door, and I'm glad they flew the picture in, because I actually knew what it is.
Okay.
This is a whole semester, guys, that we're doing in 1 month. I don't know how the heck we made it this far. Wait. The picture that Amazon sent me of my practice that got to live is literally right in that courtyard.
Should I go get it?
No, it's not. I'll go get it. I think this
That
is-
might be a good sign.
I feel like an Amazon delivery person would have to work extra hard to end up there. Like, what the heck? Hmm?
Oh, wait. Oh, no. Give me a second. Are you sure, Christian? I would love to go to science.
I mean, I'm a fan of side quests. It makes me want to hold class in the courtyard, but I don't know how we could do it. Wait, except the thing that I ordered was itself a whiteboard.
Okay, please.
Okay,
Or what? That can be a Wednesday problem.
maybe that's the
Wednesday
Wednesday.
in the
Yeah.
courtyard.
But that would be really cool. Because like, of all the things I could go and get distracted by, a whiteboard wouldn't be half bad. Okay, no, but we should finish this. Oh, but that'd be cool. Okay, so let's set this up, you guys. What do we have? Step 1, what do people want to do? What is mandated?
Well, you guys say that is conservative.
Okay, is that conservative? How do you check if that is conservative? If the curl is 0, yeah. And is it? How do we find that? That's dn, right? dm by dx minus dm by dy. Okay, and what's that?
2y minus
Yeah.
2y.
Hey, that's good, so that's 0, so yes. Okay, now we gotta actually find a potential function, so let's do that. Can I erase this so people get this now? It's good. Hi, Sylvain, yeah, you look.
I
think that's
I don't
exactly right.
understand why
What's
it's conservative.
that? Oh, because the curl is 0. Or did we do our curl wrong?
No, like why would we even do the curl?
Oh. Because the curl being 0 tells you that it comes from a gradient of a potential function.
So you took the derivative of the n part?
Oh, yeah, I took the derivative of this. So remember, this is m, this is n. So I took the x derivative of this and the y derivative of this. And if they're the same, then I have 0 curl. Make sense?
Yeah.
That's curl. Yeah? You have one?
What does conservative mean again?
Conservative means the work done is path independent. It means that the field is conservative, and what are other things we can say? Oh, it comes from a gradient. That the field is the gradient of a potential function. So if we know it's conservative, our next thing will be, well, then let's actually find that potential function. Make sense? So let's work on this from there. All right, so I'm going to erase it here. Okay. What do we have? Okay. So step 1 for finding the potential function, what do we want to do? What do you want to say? Do we want to do m or n? Your call. M? M. Okay, m is what? It's x plus y squared, and what do we know that is equal to because we have a potential function?
Partial f, partial x.
Partial f, partial x. So, the potential function must be the integral of x squared plus y d dx. And we know that is correct up to a
G of y.
g of y, some function of y. Because if we took the x derivative of all of this, we get x squared plus y. But if this had anything to do with y, that would also go to 0. Okay, so what do we have? Oh, x plus y squared? Well done, Christian. Okay, so how do we integrate with respect to x? What happens to these variables? What does this become? 1/2 x squared plus x y squared. But as far as x is concerned, y is a constant. So you just leave that y squared there for x.
G of y.
Plus g of y.
So I don't have a G of y.
Aha, brilliant. So next step. Do df by dx, which is going to be equal to d by dx of 1/2 x squared plus xy squared plus g of y. And what's that going to be? That's going to be x plus y squared. Looking good so far. Wait, did I do that right?
Oh, do you do dy? Yes.
Ah, what am I doing? Yeah, I'm a mess. D by dy. Okay. I was confused. We were ending up back what we said. Okay. Oh, do df by dy. Yeah, yeah. Y, by the way. Why do we do d by dy?
To get G of y?
Huh?
To get G of y?
To get g of y, yes, and because we know that df by dy should be equal to what if we have a conservative field, which we know we do. N, yes, the y component of the field. Beautiful. Okay, d by dy of this becomes 2xy plus dg by dy, also known as g prime of y. Are we all good? Okay, what should this be equal to, by the way? N, which was 2xy plus 3y squared. Ooh, lecture and exam theory are at work over here because look at what happened. So what is g prime of y? Right, 3y squared. Do you see how these terms, they match? That's questions.
What's G prime of y?
Ah, so g prime of y is 3y squared. G of y is integral of 3y squared dy, which is y cubed. Plus, at this point, it's just a constant in y. What's that called? A scalar, a number c. So, step 3, we got it. So in theory, f of x, y should be what? 1/2 x squared plus xy squared plus g of y, which we know is y cubed, and then plus a constant.
If we say plus c on the exam, we're getting an extra points.
If you don't say plus c, you won't lose points.
Oh.
Is that better? I don't know. All right. How do we check if this is good? Take the x derivative. What do we have if we take the x derivative? I'm going to use blue. I haven't used blue in a while. Check. So if we check this, what are we going to do?
Got it.
Yeah, so grad of f of xy, let's do that. What's the x partial? X plus y squared. Anything else? No? And then the y partial is going to be 2xy plus 3y squared. Does that track? X plus y squared plus 2xy, x plus y squared, 2xy plus 2y squared? Yes. Hooray! Very cool. Okay. Questions? Are we all good? Wow, you guys have come a long way. One more topic, and then next week, tomorrow, on Wednesday, we're gonna learn how to do all kinds of funny signal stuff, including maybe slow down the Windows XP startup sound to 1/800 its original speed. Signal processing. Okay. Questions before we end work? Oh yeah, see, sorry.
Oh, number 4?
I didn't have a bill operator. Sounds like David. Yeah, like there's a yes and you didn't need to put it. Yes, it says curl to and bill operator across.
Yeah,
It's not a secret.
Why'd you give us a 3? A 3
Because if you solve it as a scalar, I was hoping you guys would cop out and be like, oh, if you write this as scalar in R, it's a single variable problem, and that's the derivative of something.
We didn't think, no. We love our variables.
If you do it as a scalar, right, the 1 over R squared, that's just the derivative of 1 over R, or the minus 1 over R squared is the gradient, is the derivative of 1 over R. You see it? I'll show you after. Okay, guys. More questions before we move on? Okay. Okay, so this is work. Now we're going to talk about, this is Sparta. This is the part of the class where you're like, what the flux is going on, Christian?
Oh, Flux.
Bet. We're going to talk about flux. I got a Patty Christie that. It would be funny if Patty Christie said bet, I remember. I always say you bet. I've always said you bet, and now I realize it's the thing, it's bet. Okay. We're going to return to our talk on the birds and the bees, the line integrals, and then we're going to modify it. Here's our field. Arbitrary field, which has m and n as its components. And we have our path, C. Okay. We can say we're going from point A to B, that's fine by me. We might not have any path. To find work, we find the amount of our field that is parallel to our displacement. And we have known that for a while to be the following. If this is my unit tangent vector, then t hat ds, which is called dx dy, and my field, which goes like this, we know that work is integral along the path of the field dotted with the tangent direction, otherwise known as f dot dr, which is m dx plus n dy. And we are clear on where each of these pieces come from, right? This is mn, this is dx comma dy. But now we're going to talk about something else. We don't want to know how much of the field is in our direction.
We need how much is not.
Kind of. Yeah, I guess not in the perpendicular sense, sure. How much of our field is pointing out of our path rather than along it? Okay. So to do this, we're going to need to look at not the tangential direction, but the perpendicular direction, the normal direction.
Ross, the crisscrossed applesauce.
There's a crisscross applesauce thing, and now I taste the Mott's applesauce in my mouth because of the sentence. And I don't know if I'm happy or not, but I tried rice cakes for the first time yesterday. It's like oatmeal turned into crackers. But I like oatmeal, I like crackers, so I actually like them. And the redhead is now threatening to separate because of that. No, not really, but she's disappointed that my taste goes up. All right, so this is t hat. Now we're going to have n hat. All right, you guys. If I'm in 2 dimensions, there's 2 things I got to say. The first one, if I'm going in a closed path, they send me the circle because I got to figure out what I'm going to write on this exam. Maybe I just don't write it. You all get A's, right? It sounds like such a good idea. You can even say the idea has entered my mind, it has permeated, and then some sounds have come out. That's flux. Okay, if I'm traveling inward, if I'm traveling, this is the inward direction. I'm usually interested in finding what is called outward flux. So my normal vector is going to point out of the path that I'm traveling on. If I'm going here, out means this direction. So I ask you the following. If tangential is dx dy, what 2 vectors are perpendicular to dx dy? dy negative dx, right? Because the dot product has to be 0. Or, what's the other one? In general, if you want to find a vector perpendicular in 2D, this only works in 2D, you flip the components and make one of them negative. So there's 2 of these. Each of these represents a particular direction. Can you guys geometrically intuit which is which?
Negative y dx is the positive one.
Negative, oh, so you mean this one?
Oh, whoa, that's not possibly where you two.
Aha, so that's okay. So this is, I want to make sure, because I always screw up the signs of this SIG mess. I did it yesterday too. Yeah, okay, wait, cool. This one, I agree, this one is negative dy, comma dx. And this one is dy, comma negative dx. I mean, if we see that both of these are positive here, dx, dy, right? We can figure out, okay, if we flip them, the positive dy is going to have a positive x component now, so this is this one. And if I put a minus here, then this is this. This is the one that points kind of leftish. Okay, the one that we are going to use for flux is the outward, which is this one. N hat ds. Just as t hat ds, we also called dr. N hat ds, we might call dn. Okay. Everybody good so far? Yeah.
You use that one so you keep the curve on your left.
So I keep the interior on my left. Yes, excellent point. Even when it's not open, there's this notion of like inside. Why this one is a negative dy and this one's dx?
No, why like that's
Oh, so what I'm thinking is, think about the curvature of this. This looks like it's part of this kind of arc. So the inside is here. We tend to think, we want things to be positively oriented. So convention, Benjamin Franklin, the kind of people that we blame for things, says this is outward. I see.
like earlier on in the curve, it's kind of the other, like the curves, like
It does it the other way, so you just,
Oh, well, let's see, because this might be a little bit more janky. Here, t hat goes this way, right? T hat goes this way. So by that metric, you would think this goes this way, right? The normal? That's accurate, dx?
Oh,
Yeah?
do we draw the circle inward now? Outward?
I think for whatever, no, because I think the thing is to imagine that this whole thing is part of a big curve. I think I gotta clean that up a little bit more. But the convention ends up being this. So I think I gotta clean that up a little bit in my head. But this is the one that we choose for the normal differential.
So just stick with that.
Yes?
Because you could also like, if you send it, if you connect them from the bottom, you would get the opposite.
Right. So no, I think it has to be like you're always, like if I'm traveling this way, the interior must always be to my left. So therefore I must look at it like this closing this way. So we always use this for our normal. This does not change. Okay. So our work is at every point we are going to multiply our field by our instantaneous displacement. Our flux is going to be, at every point we're going to multiply our field. We're going to dot our field with our normal component to our path. So what does that look like? That looks like flux is the integral along the path, always along the path, of f dot n hat ds, otherwise known as f dot dn. And again, the field is mn dotted with, what did we say dn was? dy negative dx. So, what do we get at the end? M dy minus n dx. Along the path. That is flux. That is the definition of flux along the path. It is the analog to work. So this is not tangential, but now perpendicular, or it's called normal.
But we're still treating it like the other integral before. Once we get there, now it's just.
Now it's a line integral, and we all know how to solve those. See? Oh, that's just the symbol, yeah.
Capital
Is that capital 5?
It's capital 5.
Capital 5. Now
You then make me come back.
oh, now I want to do the Deathly Hallows. What's the Deathly Hallows in Harry Potter? That?
So this is like, can you correlate this to the actual flux that we see in that?
Yeah, this is that. This is that. That's exactly it. Because in the NM, you're trying to find the electric flux, right? The field coming out of a region. That's what this is. Okay, so that is flux. If I give you this line integral, are you able to solve it? What is still the same approach? What do? Parametrization, and you're off to the races. What was that?
Sharp plugging.
Sharp.
So I just say sharp plugging, like you plugging literally everything you can.
There you go.
This is kind of like the opposite of curl.
Yes, and that's a really good point, guys. When you think of curl, draw curl for me with your arms. So go on. Okay. Now draw divergence. Draw divergence. Raise the roof. Yes. Oh, there you go. I love it. You got it. Yeah. Okay. We're expanding. The universe is expanding, right? I don't feel like I'm expanding in certain ways. At least my brain feels like it expands at the point where it explodes sometimes. That's exactly it. So, work is related to curl. Flux is going to be related to who's the actress? Jennifer Lawrence. Right? Or no, different book series. Sorry. No. Divergent? Is that?
Oh!
No, she does Hunger Games, right?
Cat is
Is it the same actress? Is it the same? No, not the same author. What the heck am I
Not the
doing?
same quality.
Not the
It's
same
not the same.
at all.
Oh, Divergence is way better than Hunger Games.
I will cut you
Yeah.
out of this room. One of them is the foundational term. The other one, it's.
Was that a bad time?
Yeah, we're talking about it.
What did he say?
It's literally like writing fan fiction about her own book series as like a passion.
She's feeding to
Yes. There's a.
I think they're both being
I'm
serious.
feeding for the math.
Or the divergence of the curl.
Searching for
Well,
traffic.
are we talking about math diversions or like, I don't know.
It's really bad.
If the flux occurs.
I think Hunger Games is really worse.
If flux
Flux is related to the divergence.
I think actually if not necessarily because we can have a field that has some curl and some divergence. It doesn't have to be each one or the other. But as long as it has some curl, it's no longer conservative. Alright, guys, so this is going to be our chart. This is our chart for work. This is our chart for flux. I don't have a salsa for it. Oops. Alright, integral along the path of f dot d n. As it turns out, whether or not the field is conservative, we're not going to, well actually, hang on. No, hold on. We don't care about whether or not the field is conservative. Here we're only going to see if we have an open path or a closed path. If our path is open, we have the most general possible case. We have integral along the path of m dy minus n dx. And again, this is along the path, so we're going to parameterize. Okay, just like here. But the line integral is different because we have things in a different order, but it's the same process to solve. If we have a closed path, for work, this was the area, this was the integral over the interior of the curl of the field.
But now we can do Green's theorem. Stokes' theorem!
No, Stokes' is actually Green's tangential for surfaces. That's the whole thing.
I tried.
Yeah, no, that's a fun one. We're not going to do it in this class, but maybe Evan did or is going to do a session on it. Did you do a session on this at some point?
You see, at that point, I need
We will catch Evan. So, oh, hi Evan.
along
Did you do a session on Stokes' and all that, or was that mythology?
Yeah.
Oh, cool. Okay, cool. All right. So this is what happens for flux. For a closed path where all of the criteria here are met as well, we say that this is the integral of dm dx plus dn by dy.
Wait, that's just a double derivative if it's a potential function.
Oh, I mean, yes. Yes, actually, there's a little thing there too, but that we're not going to. Yeah, that's all right. But no, this is called the divergence of f, also known as div of f. So we'll talk briefly about divergence too, but are there any questions so far? This is called Green's normal. The normal form of Green's theorem.
Like normal is in
Yes, normal as in
Not as in
perpendicular,
normal as in-
not as in ordinary, right, right. The normal as in,
Normally Green found this by using normal.
yeah, normally I teach this in a week and I'm doing it in 10 minutes. Green's abnormal theorem. All right, guys. Please ask questions. None of this is supposed to be out of hand.
conservative fields have divergence.
Can conservative fields have divergence? I'm so happy you asked that.
Why don't we find out?
Why don't we find out?
If the conservative field is the grad of f, and we dotted it with the del operator, then we feel like we can this.
Then what are we going to do? We're going to do what? We're going to
Dot
do
it with the del operator.
d by dx of df by dx plus d by dy of dx by dy. That's just the sum of the second derivatives, right? fxx plus fyy. So what was the question again? I forget.
Can we do it with a?
Do conservative fields have zero divergence? What was it? What was it that you asked me?
Do conservatives have divergence?
They do.
And that's how we should, because those.
In fact, that conservative fields are the most divergent ever. What was an example of a conservative field you guys saw on the P set? Gravity, right? How does gravity work? Well, like this. Those are very conservative, yeah. The moment they have any bit of rotationality, they are no longer conservative. Now, here's a question. And this is inspired by what Lily was saying. If a field has curl, can it also have some divergence? If a field has some divergence, can it also have curl? Or does having one mean you don't have any of the other?
Well, if the curl is across the divergence, if the curl is really high, then the dot's really low, because it's like perpendicularity versus parallelity.
That's a cool way to think about it. You can have both. You can have both simultaneously. If you have a lot of one, you have less of the other, right? If your field goes all the way like this, what does it have nothing of? No curl. If your field goes all the way like this, nothing is exiting.
There's all curl, no divergence.
Right. Generally, though, you have a mix.
So if it were like this, like a spiral inside, that would have
Zero divergence.
But if it's like spiral inside, like,
Oh, like a, so not just rotating,
but like spiraling inward.
so you're saying somehow where like the radius of curvature gets smaller?
Yeah.
That's an interesting one.
I have a slight idea.
I don't think that has divergence. But that's from my drawing. We could calculate it, yeah.
I have a slight idea.
Uh-huh.
Let me help us. Well, if the curl is the del operator crossed with your gradient, that's a sine of theta, the 2 magnitude sine theta. If you do the divergence, that's the cosine of theta. And you always know that cosine and sine by the angles.
Oh, you're saying like with the equation of like a
Yeah,
spiral?
just even in the general sense.
Huh.
And so when the sine is 0, the cosine's at its maximum. Vice versa.
So you're saying no divergence?
No divergence is maximum curl.
Yeah. That we know. Yeah. Uh-huh.
I have to go down for lowest setting.
Yes. Yeah, that's a little bit of show. Yeah. That's a good point. Okay, guys. Fundamentally, when we're trying to find the work done in a closed region, we are adding up all the little amounts of swirliness going on inside. So when we're trying to find the flux for a closed region, we are adding up, if we have a closed path C that meets all of our criteria, we are adding up all of the sort of explosiveness inside of our path. Think of biology, cells, osmosis, diffusion, that kind of thing. And if you take E&M, you find this as well. Okay. So that is actually, let me see. We know how to find potential functions. Yeah. We might be done. Do you want to be done? Okay, I have one more thing. Sometimes your path is not closed. Chalk's going to get in my eye. because I've just been working a lot with chalk. Achoo! Sometimes the path that you are asked to find work or flux along is not closed. But if it were closed, it would be a much easier thing to do. Huh? Can you make it closed? And then what's the only thing that you owe? I'm going to draw something. So this is a good one. This is a good one. Ow, this chalk from when I'm erasing is getting in my eyes.
Wait, is he actually? No. Oh, he's already.
I don't know what you're talking about over here.
I'm getting it.
Okay, everyone, let's say that I asked you for the work done in going along, what's a good example? Okay, yeah. If I asked you for the work done in going along this path. No. If I asked you for the work done in going along this arc, is this a closed path? Is it a closed path? It's just this segment, right? We're going from here to here. So we want integral over c of f dot dr. Wow, even the chalk says, Christian, that's enough. All right. But here's the thing, you guys. This would be a much easier thing to find if I could do what? If I could connect these regions, right? So if I could connect these paths. So if I had an extra color, oh, green, I wonder why I would want it to be green. Oh, I still got it. And I wanted to call this, what do you want to call it? C1. Well, if my path were C plus C1, what could I use? I could use Green's theorem, right? So I know that the line integral over C plus C1 of f dot dr, which is the same as the individual line integrals over the C part plus what? Plus the C1 part. But if I do have it closed, what do I also know this is equal to? Double integral of the curl over this interior R. Hey, this isn't half bad, because this region and the curl of this field, let's say, are very easy to find. Then, let's say that I do my work and I find the result, and I find this. Because I like curl, I like double integrals, and this region and this field were interesting, were easy. Then, how do I find the work done through C? Subtract the work done through C1. That is to say, integral over C of f dot dr is integral over C plus C1 f dot dr minus integral over C1. Because I can find this one using Green's. That is a very convenient use case for Green's theorem. Okay. Salud. Questions? Okay. I see. It can be any path. That's a really good question. Why would this be an easy one to do? Why would I look at this and be like, oh, I definitely want to use Green's? Yeah, so this is a really easy path. This is y equals 0, dy equals 0, and x goes from this to this. That's going to be a really, really easy line integral. So not much skin off on it.
Wait, so you're using Green's for the entire thing?
I'm using Green's for the entire thing, and then what do I need to do if I just want it for this guy?
Subtract it.
Subtract the one here for here. But that means I get to do an easy double integral and a really easy line integral instead of a parameterization about this guy. Okay. More questions? I don't. Say again? What do we Oh, about divergence and flux. Can you find divergence? Can you find flux? Then if you can, you're good. But like, can you find divergence? Can you find? Oh, you're saying how can we find it? That was a very useless answer to your question. You need to be able to find divergence, and you need to be able to do flux, even when you can't use Green's theorem. So basically this. Can you do this line integral? And can you do this if you identify the case where you can use it? Okay, more questions. Okay. Yeah. Same criteria as for the same criteria. All right. The criteria for Green's theorem.
No.
Oh.
I mean, I'm forcing answers.
Oh, okay. Shield his eyes. All right. You have more questions, you guys? Hi. Hi. Correct. The field isn't defined inside the region. Okay. Hi, Vaughn.
What does flux mean again?
Flux is how much of the field is coming out of your path, whereas work is how much of your field is going along your path.
So what is the significance of that?
Wait, say a little louder.
What is the significance of that?
The significance of that is usually if you have some quantity, like think about fields in your life, gravity or electrical, and you want to figure out how much of that is permeating or how much of something is exiting out. Usually it's a closed region, then you use this.
When Bon is trying to go to Hive and people can, and he, sorry.
No, you're very good.
We were doing the pizza, we used the Roblox for an example, trying to remember what, it was really bad.
It's funny, I'd like to see that.
No, don't see it.
No?
We got nowhere. We got nowhere.
So guys, in summary for today, can you find a potential function? Can you use Green's theorem to find work by using curl? Can you use Green's theorem to find flux by using divergence? And can you find flux for a general region? And lastly, when I got chalk in my eye, the bit was, can you use Green's to simplify a line integral and then do a little bit of bookkeeping to remove the piece that you added to close the region? Okay. More questions? What's up, Diego?
Oh, nothing. Just,
A lot going on?
yeah.
I'm sorry. It'll be all right, guys.
Are we free to see our families now?
Yeah, I gotta go see my whiteboard. So yes, on Wednesday, pay attention because what we talk about on Wednesday will still be tested. We're just not gonna give you a complicated problem about it. It'll be like a true or false or like a conceptual. It'll be fun. Okay. Find if you got questions after class, other than that, and go enjoy chemistry. There'll be memes and debates for me. I'm glad you got to see it. Yeah, I wonder what yours is going to have. There's a ring committee every year.
Who still has his passport?
Oh, it's all about it. You got to pay for it.
I'm gonna ask you, talking about like
Yeah, that's true. Because that tends to work better when you're in free. I'm giving you guys like the big you might even think the Dell makes it easier. I bet that's what Dale would say.
We ever decided to just like talk into the camera? Stand up, give like a pep talk.
I guess.
This is being recorded now.
I need to watch the Flux first.
It was minus G M over R squared, right? R half. And so maybe I took a cop out in this, but I'm saying, hey guys, because we think of like R comes from X, Y, and Z, sure, right? Or from X, Y, and Z. Yeah, from X, Y, and Z. This should be rho, but this was, but regardless, okay, but if you do the scalar form, you agree that the field is just G M over R squared. This is the direction. So the scalar version is this. Now the question is, can you show that this is the derivative with respect
Oh,
to R
shoot.
of something.
This fella made
And
30
the answer is
questions
if
through
you
the
integrate this
workshop.
with respect to R, what are you gonna get? Yep, and the negative cancels it. So you get this, so you can show that this comes from this. And all I really want in the piece, and I agree that wasn't clear. But you can just make this case and be like, yeah, Christian, it's true, you don't go through this and that stuff. That would have sufficed.
If you want to make that clear, I think maybe don't restate this R in terms of X, Y, Z.
Let me put that in my notes for next week. Yeah, that's
Can
really good point.
can we see what?
I'm with you.
We won't have to use the down on the midterm. If I find myself with the urge, I should be like, stop.
Well, but it might make your life easier, so that works out. You want to put,
Dare programming there,
Okay,
like, just say that.
Beautiful.
Neutron.
These are 5 pages of questions.
Okay,
Am I really gonna print
all right.
out like?
You all can see them? Okay,
Am
sure.
I really gonna print out like 100 pages tomorrow?
So like,
I don't know if I can carry all of that.
Wait, what?
Because the workshop is
so like with
5
this,
pages.
adding the second purchase.
If we have
It
a,
just
so first off,
this.
we have to ask ourselves, what does this measure? Just as curl measure the rotationality of a field, divergence measures how much a field is pointing outward, radially outward. So this field, remember like on the P set, this one had 0 curl, this one has all of the divergence. So if you have a closed path, right? If you have a closed path, the amount of your field that points out of your path, right, is the same as the amount of expansion happening inside of your region. Does that make sense?
Yeah.
Okay, so that's the English version. Does that help? You still have questions, Sharif? That's what I'm asking.
So why?
The shark's judge panel.
This is like DMDX
What?
is like the second
The panel.
your best X root.
But we don't know that it's conservative. This has nothing to do with it being